In statistics, the Mann-Whitney U test, Wilcoxon rank sum test, or Wilcoxon-Mann-Whitney test, is a nonparametric test of the null hypothesis that two populations are the same against an alternative hypothesis, especially that a particular population tends to have larger values than the other. It has greater efficiency than the t-test on non-normal distributions, such as a mixture of normal distributions, and it is nearly as efficient as the t-test on normal distributions. The Wilcoxon rank sum test is not the same as the Wilcoxon signed rank test, although both are nonparametric and involve summation of ranks. Assumptions and formal statement of hypotheses. Although Mann and Whitney developed the MWW test under the assumption of continuous responses with the alternative hypothesis being that one distribution is stochastically greater than the other, there are many other ways to formulate the null and alternative hypotheses such that the MWW test will give a valid test. A very general formulation is to assume that all the observations from both groups are independent of each other, the responses are ordinal, the distributions of both groups are equal under the null hypothesis, so that the probability of an observation from one population exceeding an observation from the second population equals the probability of an observation from Y exceeding an observation from X. That is, there is a symmetry between populations with respect to probability of random drawing of a larger observation. Under the alternative hypothesis, the probability of an observation from one population exceeding an observation from the second population is not equal to 0.5. The alternative may also be stated in terms of a one-sided test, for example, p, za y, a plus a 0.5 p, za equals a y, a 0.5. Under more strict assumptions than those above, for example, if the responses are assumed to be continuous and the alternative is restricted to a shift in location equals AF2, ZA plus AI, we can interpret a significant MWW test as showing a difference in medians. Under this location shift assumption, we can also interpret the MWW as assessing whether the Hodge-Gieser-Layman estimate of the difference in central tendency between the two populations differs from zero. The Hodge-Gieser-Layman estimate for this two-sample problem is the median of all possible differences between an observation in the first sample and an observation in the second sample. Calculations. The test involves the calculation of a statistic, usually called U, whose distribution under the null hypothesis is known. In the case of small samples, the distribution is tabulated, but for sample sizes at the V20 approximation using the normal distribution is fairly good. Some books tabulate statistics equivalent to U, such as the sum of ranks in one of the samples, rather than U itself. The U test is included in most modern statistical packages. It is also easily calculated by hand, especially for small samples. There are two ways of doing this. First, arrange all the observations into a single rank series. That is, rank all the observations without regard to which sample they are in. Method 1. For small samples a direct method is recommended. It is very quick, and gives an insight into the meaning of the U statistic. Choose the sample for which the ranks seem to be smaller. Call this sample 1, and call the other sample sample 2. For each observation in sample 1, count the number of observations in sample 2 that have a smaller rank. The sum of these ranks is U. Method 2. For larger samples, a formula can be used. Add up the ranks for the observations which came from sample 1. Where there are tied groups, take the rank to be equal to the midpoint of the group. The sum of ranks in sample 2 is now determinate, since the sum of all the ranks equals n, NA plus A1/2 where n is the total number of observations. U is then given by where n1 is the sample size for sample 1, and A1 is the sum of the ranks in sample 1. Note that it doesn't matter which of the two samples is considered sample 1. An equally valid formula for U is the smaller value of U1 and U2 is the one used when consulting significance tables. The sum of the two values is given by knowing that A1 plus A2 equals AN, NA plus A1/2 and N equals AN1 plus AN2 and doing sum algebra, we find that the sum is. Properties. The maximum value of U is the product of the sample sizes for the two samples. In such a case, the other U would be 0. Examples, illustration of calculation methods. Suppose that Aesop is dissatisfied with his classic experiment in which one tortoise was found to beat one hare in a race, and decides to carry out a significance test to discover whether the results could be extended to tortoises and hares in general. He collects a sample of 6 tortoises and 6 hares, and makes them all run his race at once. The reversed order in which they reach the finishing post is as follows, writing T for a tortoise and H for a hare. THHHHHTTTTTH. What is the value of U? Using the direct method, we take each tortoise in turn, and count the number of hares it is beaten by, getting 1, 1, 1, 1, 1, 6, which means U equals 11. Alternatively, we could take each hare in turn, and count the number of tortoises it is beaten by. In this case, we get 0, 5, 5, 5, 5. 5. So U equals 0 plus 5 plus 5 plus 5 plus 5 plus 5 equals 25. Note that the sum of these two values for U is 36, which is 6AA, A6. Using the indirect method, the sum of the ranks achieved by the tortoises is 1 plus 7 plus 8 plus 9 plus 10 plus 11 equals 46. Therefore U equals 46AAA, 6A. 7 closing round bracket over 2 equals 46 a 21 equals 25. The sum of the ranks achieved by the hares is 2 plus 3 plus 4 plus 5 plus 6 plus 12 equals 32, leading to U equals 32 AAA 21 equals 11. Illustration of objective test, a second example race, with 19 participants of each species, in which the outcomes are as follows. The median tortoise here comes in at position 19, and thus actually beats the median hare, which comes in at position 20. However, the value of U is 100. 0 tortoises, plus 10 tortoises, equals 0 plus 100 equals 100. Value of U, for tortoises, is 261. Plus equals 90 plus 171 equals 261, consulting tables, or using the approximation below, showed that this U value gives significant evidence that hares tend to do better than tortoises. Obviously this is an extreme distribution that would be spotted easily, but in a larger sample something similar could happen without it being so apparent. Notice that the problem here is not that the two distributions of ranks have different variances. They are mirror images of each other, so their variances are the same, but they have very different means. Normal approximation, for large samples, U is approximately normally distributed. In that case, the standardized value, where mu and I mu are the mean and standard deviation of U, is approximately a standard normal deviate whose significance can be checked in tables of the normal distribution. Mu and I mu are given by, and. The formula for the standard deviation is more complicated in the presence of tied ranks. The full formula is given in the textbooks referenced below. However, if the number of ties is small, ties can be ignored when doing calculations by hand. The computer statistical packages will use the correctly adjusted formula as a matter of routine. Note that since U1 plus U2 equals N1AN2, the mean N1AN2/2 used in the normal approximation is the mean of the two values of U. Therefore, the absolute value of the Z statistic calculated will be same whichever value of U is used. Effect sizes. It is standard practice among scientists to report an effect size for an inferential test. Common language effect size. One method of reporting the effect size for the Mann-Whitney U test is with the common language effect size. As a sample statistic, the common language effect size is computed by forming all possible pairs between the two groups, then finding the proportion of pairs that support a hypothesis. To illustrate, in a study with a sample of 10 hares and 10 tortoises, the total number of pairs is 10 times 10 or 100 pairs of hares and tortoises. Suppose the results show that the hare ran faster than the tortoise in 90 of the 100 sample pairs. In that case, the sample common language effect size is 90%. This sample value is an unbiased estimator of the population value. so the sample suggests that the best estimate of the common language effect size in the population is 90%. Rank biserial correlation, a second method of reporting the effect size for the Mann-Whitney U test is with the rank biserial correlation. Edward Curitan introduced and named the measure. Like other correlational measures, the rank biserial correlation can range from -1 to +1, with a value of 0 indicating no relationship. Dave Kirby introduced the simple difference formula to compute the rank biserial correlation from the common language effect size. The correlation is the difference between the proportion of pairs that support the hypothesis minus the proportion that do not. Stated another way, the correlation is the difference between the common language effect size and its complement. For example, consider the example where hares run faster than tortoises in 90 of 100 pairs. The common language effect size is 90%, so the rank biserial correlation is 90% minus 10%, and the rank biserial R equals 0.80. Hans Wendt described a formula to compute the rank biserial from the Mann-Whitney U and the sample sizes of each group, R equals 1 /. This formula is useful when the data are not available, but when there is a published report, because U and the sample sizes are routinely reported. Using the example above with 90 pairs that favor the hares and 10 pairs that favor the tortoise, U is the smaller of the two, so U equals 10. The Wendt formula is then R equals 1 / equals 0.80, which of course is the same result as with the Kirby simple difference formula. Relation to other tests, comparison to students' t-test, the U-test is more widely applicable than independent sample students' t-test, and the question arises of which should be preferred. Ordinal data, U remains the logical choice when the data are ordinal but not interval scaled, so that the spacing between adjacent values cannot be assumed to be constant. Robustness, as it compares the sums of ranks, the Mann-Whitney test is less likely than the t-test to spuriously indicate significance because of the presence of outliers. That is, Mann-Whitney is more robust. Efficiency, when normality holds, MWW has an efficiency of or about 0.95 when compared to the t-test. For distributions sufficiently far from normal and for sufficiently large sample sizes, the MWW is considerably more efficient than the t. Overall, the robustness makes the MWW more widely applicable than the t-test, and for large samples from the normal distribution, the efficiency loss compared to the t-test is only 5%. So one can recommend MWW as the default test for comparing interval or ordinal measurements with similar distributions. The relation between efficiency and power in concrete situations isn't trivial though. For small sample sizes one should investigate the power of the MWW versus T. MWW will give very similar results to performing an ordinary parametric two-sample t-test on the rankings of the data. Area under curve statistic for ROC curves, the U statistic is equivalent to the area under the receiver operating characteristic curve that can be readily calculated. Because of its probabilistic form, the U statistic can be generalized to a measure of a classifier's separation power for more than two classes. Where C is the number of classes, and the term of considers only the ranking of the items belonging to classes K and L according to the classifier's estimates of the probability of those items belonging to class K. Will always be 0 but, unlike in the two-class case, generally, which is why the measure sums over all pairs, in effect using the average of and different distributions. If one is only interested in stochastic ordering of the two populations, the U-test can be used even if the shapes of the distributions are different. The concordance probability is exactly equal to the area under the receiver operating characteristic curve that is often used in the context. Alternatives: if one desires a simple shift interpretation, the U-test should not be used when the distributions of the two samples are very different, as it can give erroneously significant results. In that situation, the unequal variances version of the t-test is likely to give more reliable results, but only if normality holds. Alternatively, some authors suggest transforming the data to ranks and then performing the t-test on the transformed data, the version of the t-test used depending on whether or not the population variances are suspected to be different. Rank transformations do not preserve variances, but variances are recomputed from samples after rank transformations. The Brownian-Forsythe test has been suggested as an appropriate non-parametric equivalent to the F-test for equal variances. History: the statistic appeared in a 1914 article by the German Gustav Deutschler. As a one-sample statistic, the signed rank was proposed by Frank Wilcoxon in 1945, with some discussion of a two-sample variant for equal sample sizes, in a test of significance with a point null hypothesis against its complementary alternative. A thorough analysis of the statistic, which included a recurrence allowing the computation of tail probabilities for arbitrary sample sizes and tables for sample sizes of 8 or less, appeared in the article by Henry Mann and his student Donalda Ransom Whitney in 1947. This article discussed alternative hypotheses, including a stochastic ordering. This paper also computed the first 4 moments and established the limiting normality of the statistic under the null hypothesis, so establishing that it is asymptotically distribution-free. Related test statistics: Kendall's I, the U-test is related to a number of other non-parametric statistical procedures. For example, it is equivalent to Kendall's I correlation coefficient if one of the variables is binary. I statistic, a statistic called I that is linearly related to U and widely used in studies of categorization, and elsewhere, is calculated by dividing U by its maximum value for the given sample sizes, which is simply N1AA, AN2. I is thus a non-parametric measure of the overlap between two distributions. It can take values between 0 and 1, and it is an estimate of P, YA x, A plus A 0.5 a P, YA equals an X, where X and Y are randomly chosen observations from the two distributions. Both extreme values represent complete separation of the distributions, while AI of 0.5 represents complete overlap. The usefulness of the I statistic can be seen in the case of the odd example used above, where two distributions that were significantly different on a U-test nonetheless had nearly identical medians. The O value in this case is approximately 0.723 in favor of the hares, correctly reflecting the fact that even though the median tortoise beat the median hare, the hares collectively did better than the tortoises collectively. Example statement of results: in reporting the results of a Mann-Whitney test, it is important to state a measure of the central tendencies of the two groups, the value of U, the sample sizes, the significance level. In practice, some of this information may already have been supplied and common sense should be used in deciding whether to repeat it. A typical report might run: median latencies in groups E and C were 153 and 247 milliseconds. The distributions in the two groups differed significantly. A statement that does full justice to the statistical status of the test might run: outcomes of the two treatments were compared using the Wilcoxon-Mann-Whitney two-sample rank sum test. The treatment effect was quantified using the Hodgkiss-Lehmann estimator, which is consistent with the Wilcoxon test. This estimator is the median of all possible differences in outcomes between a subject in Group B and a subject in Group A. A non-parametric 0.95 confidence interval for Lee accompanies these estimates, as does I, an estimate of the probability that a randomly chosen subject from population B has a higher weight than a randomly chosen subject from population A. The median, quartiles weight for subjects on treatment A and B respectively are 147, 121, 177, and 151, 130, 180, kg. Treatment A decreased weight by Lee equals 5 kilograms. However, it would be rare to find so extended a report in a document whose major topic was not statistical inference. Implementations: in many software packages, the Mann-Whitney test has been poorly documented. Some packages incorrectly treat ties or fail to document asymptotic techniques. A 2000 review discussed versions of the following packages. MATLAB has ranksum within its statistics toolbox. R statistics base package implements the test Wilcox test and in its COIN package. SAS implements the test in its PROCNPA one-way procedure. Starter implements the test in its ranksum command. Python has an implementation of this test provided by SciPy. 1, See also, Kolmogorov test, Wilcoxon signed rank test, Kruskal-Wallace one-way analysis of variance. Notes. References, Lehman, Eric L. Nonparametrics, Statistical Methods Based on Ranks. Further reading, Hetmansberger, Tia P. McKean, J. W. Robust Nonparametric Statistical Methods. Kendall's Library of Statistics 5nd ed. London. New York, Edward Arnold. John Wiley & Sons, A Incorporated pp. As-if plus 467. ISBN A0-340-54937-8. MRA 1604954. Hodges, J. L. Lehman, E. L. Estimation of location based on ranks. Annals of Mathematical Statistics 34, 598 Euro 611 doi, 10.12141177704172. JSTORA 2238406. MRA 152070. ZBLA 0203.21105. P. Euclid Ohms/1,177,704,172. Lehman, Erika L. Nonparametrics, Statistical Methods Based on Ranks. With the special assistance of H. J. M. Dobera. New York, Springer PPXVI plus 463. ISBN A978-0-387-35212-1. MRA 395032. Oja, Hanu. Multivariate Nonparametric Methods with R, an approach based on spatial signs and ranks. Lecture Notes in Statistics 199. New York, Springer pp. As-if plus 232 doi, 10.1007/978-1-4419-0468-3. ISBN A978-1-4419-0467-6. MRA 2598854. Sen, Pranaba. On the Estimation of Relative Potency and Dilution, Direct, Essays by Distribution-Free Methods. Biometrics 19, 532 Euro 552 doi, 10.2307/2527532. JSTORA 2527532. ZBLA 0119.15604. External links, Table of Critical Values of U, Interactive Calculator for U and its Significance.